Okay, well, welcome back to our class on college physics. We're continuing to make some good progress. And so now at this point, we completed these first two sections, the sections on mechanics, which had quite a number of topics that we addressed. And then we spent 3 lectures talking on thermodynamics. And now we're going to get into this fourth area where we'll start to talk about vibration and waves. So let's go on to topic number 13. And perhaps you've seen these kind of patterns if you were to throw rocks into a pond or see it slowly rain on some water, standing water, that you would see these kind of waves that start to migrate out from a central point of where that starts. As is the usual case, we'll have some reading review questions that I'll go over quickly. We'll go over the main topic material. That'll include some questions that we'll quickly go over, and then we'll have a summary. So here's our first question is, so suppose that a grandfather clock is calibrated correctly at sea level and then is brought up to the top of a tall mountain. What would need to be done to calibrate the clock at the top of the mountain? So the answer is the bob on the pendulum should be slid slightly up the rod. Okay, which of these represents an example of simple harmonic motion? And the answer is 2 and 3, a marble rolling back and forth in a concave bowl and a tree branch vibrating. For which of the following would it be most advisable to utilize a system that is damped? The answer is within shock absorbers. And so which of the following is true for an oscillating spring? The answer is that the potential energy is greatest when the spring is the most compressed and the most extended. Which of the following statements are true? And the answer is 1 is true, but 2 is false. And consider a rope hung from the top of a tall ceiling to the ground. Someone sets up waves from the bottom of the rope and watches as they propagate up the rope. The waves speed along the vertical rope will, and the answer is, increase with vertical position up the rope. For which of the following will the phenomena of wave interference apply? And the answer is all of the above. Okay, well, we're going to be talking about vibrations and waves. And from masses on springs to vibrations of atoms, we are surrounded by periodic motion. In this section, we will look more closely at Hooke's law, which, as you may recall, says that the force is proportional to the displacement, which means there is a tendency for objects to be restored to some equilibrium position. Many physical systems can be modeled with this idea, such as vibration of strings, the swinging of a pendulum, and the propagation of all kinds of waves. Periodic vibration can cause disturbances that move through a medium as waves. There are many kinds of waves in nature: sound waves, water waves, seismic waves, and electromagnetic waves. So let's consider Hooke's law. And so in this figure, we see that the force exerted by a spring on an object varies with the displacement of the object from the equilibrium point x equals 0. So let's imagine a block attached to a spring moving on a frictionless horizontal surface. If the spring is stretched or compressed a small distance x from its unstretched or equilibrium position and then released, it exerts a force on the object, as you can see in the figures. In 1678, Robert Hooke performed experiments using springs and found that the spring force F sub s obeyed the equation shown, where x is the displacement of the objects from its equilibrium position. And K is a positive constant called the spring constant. This is known as Hooke's law. The value of K is a measure of the stiffness of the spring. Stiff springs can have large K values and soft springs have small K values. Notice that the negative sign in the equation, it means that the force exerted by the spring is always directly opposite the displacement of the object. If the figure in the figure on the left, the block is to the right of the equilibrium position, so x is positive and F sub s is negative. This means that the force is in the negative direction to the left. In the middle figure, the object to the left of the equilibrium position, so x is negative and f of s is positive, indicating that the direction of the force is to the right. Of course, when x equals 0, as in the right-hand figure, the spring is unstretched and f sub s equals 0. Because the spring force always acts towards the equilibrium position is sometimes called a restoring force. A restoring force always pushes or pulls the object towards the equilibrium position. Let's say that the block is initially pulled a distance a to the right and released from rest, as shown in the figure on the left. The force exerted by the spring pulls the block back towards the equilibrium position. So x is decreasing, which means that the magnitude of the force is decreasing. The block gets faster as it moves towards x equals 0. And as its speed is a maximum just when it passes through the equilibrium position. The middle figure, momentum causes a block to overshoot at the equilibrium position and compress the spring. Now the block is moving to the left of the equilibrium position where the value of x is negative and the spring force acts on it to the right. The force increases the further the block gets from x equals 0 and the speed decreases. The block finally comes to rest at x equals minus a, the figure on the right, then accelerates back towards x equals 0 and eventually returns to the original position at x equals a. The process is repeated and the block continues to oscillate back and forth. This type of motion is called a simple harmonic motion. Simple harmonic motion occurs when the net force along the direction of motion obeys Hooke's law, when the net force is proportional to the displacement from the equilibrium point and is always directed towards the equilibrium point. Not all periodic motion over the same path can be classified as a simple harmonic motion. For example, think of a ball being tossed back and forth between two people. The ball moves repetitively, but the motion isn't simple harmonic motion because the force acting on the ball doesn't take the form of Hooke's law. So here, in this figure, we're wanting to determine the spring constant. Because the upward spring force balances the weight when the system is in equilibrium, it follows that K equals mg divided by d. Think about an object suspended from a vertical spring. The motion is simple harmonic. In this case, the force of gravity on the object stretches the spring until equilibrium is reached and the object is suspended at rest. By definition, the equilibrium position of the object is x equals 0. When the object is moved away from equilibrium by a distance x and released, the net force acts towards a pendulum position. Because the net force is proportional x, the motion is simple harmonic. So here are three basic concepts that are important when we discuss any kind of periodic motion. First is the amplitude A. It is the maximum distance of the objects from the equilibrium position. In the absence of friction, an object in simple harmonic motion oscillates between the position of x equals minus a to x equals plus a. The period t is the time it takes the object to move through one complete cycle of motion from x equals a to x equals minus a and back to x equals a. And finally, the frequency f is the number of complete cycles of vibrations per units of time. Frequency is a reciprocal of the period. So we can use Hooke's law and Newton's second law to find the acceleration of an object moving in simple harmonic motion. This equation for the acceleration is an example of a harmonic oscillator equation, which gives the acceleration as a function of position. Because the maximum value of x is defined to be the amplitude a, the acceleration ranges over the values of minus ka over m to plus ka over m. So here's a question. So a block at the end of a horizontal spring is pulled from equilibrium at x equals 0 to x equals a and release. Through what total distance does it travel in one full cycle of motion? And the answer is 4a. And so to complete a full cycle of oscillation, the object must travel a distance 2a to position x equals minus a, and then travel an additional distance to a, returning to the original position at x equals plus a. So for a simple harmonic oscillator with the following pair of vector quantities, can't both point in the same direction? That is, the position vector is the displacement from equilibrium. And so the answer is position and acceleration. So the force producing harmonic oscillation is always directed towards the equilibrium position and hence directed opposite to the displacement from the equilibrium. The acceleration is the direction of the force, thus it is always directed opposite to the displacement from equilibrium. Okay, so let's talk about elastic potential energy. So a ball projected from a spring-loaded gun is what we have in this figure. And so the elastic potential energy stored in the spring is transferred from the kinetic energy of the ball into the kinetic energy of the ball. As you may know, the energy stored in a stretched or compressed spring or some other elastic material is called the elastic potential energy, PE sub S. The figure shows a ball being projected from a spring-loaded toy gun. The spring is initially compressed a distance x. When the gun is fired, the compressed spring does work on the ball and impacts kinetic energy to it. So let's apply the law of conservation of energy, include both gravitational and spring potential energy in non-conservative forces like friction. If non-conservative forces like friction are present, then the changes in mechanical energy must equal the work done by the non-conservative forces. Keep in mind that we need to include rotational kinetic energy in both of these equations for systems involving torques. So in this figure, we have a block sliding on a frictionless horizontal surface that collides with a light spring. In the absence of friction, the mechanical energy in this process remains constant. So if we take a look at the figure, a block of mass m slides on a frictionless horizontal surface with constant velocity v sub I. The total energy of the system and the kinetic energy, the total energy of the system is the kinetic energy of the block. So in this figure, for our discussion, let's assume that the spring is very light and it's an ideal spring, and so it has negligible kinetic energy. As a block collides with the spring is compressed and it exerts a force to the left on the block. Now the block has kinetic energy 1/2 mv squared, where v is less than v sub I, and the spring has potential energy 1/2 k x squared. So when the block stops for an instant at the point of the maximum compression, the kinetic energy is 0. And so because the spring force is conservative and because there are no external forces that can do work on the system, the total mechanical energy of the system consists of the block and the spring remains constant. Energy is transformed from the kinetic energy of the block to the potential energy stored in the spring. So as the spring expands, the block moves in the opposite direction and regains all the initial kinetic energy. So here we're seeing an elastic potential energy that is stored in this drawn bow. And so we have a photo of an archer, and when she pulls back on the bowstring, elastic potential energy is stored in both the bent bow and the stretched bowstring. When the archer releases the arrow, the potential energy stored in the system is transformed into kinetic energy of the arrow. Crossbows and slingshots work in the same way. So let's look at this question. When an object moving in simple harmonic motion is at its maximum displacement from equilibrium, which of the following is at maximum? And the answer is acceleration. In simple harmonic motion, the force and hence the acceleration is directly proportional to the displacement from equilibrium. Therefore, force and acceleration are both at a maximum when the displacement is a maximum. So let's talk about velocity as a position, as a function of position. So in this figure, in figure A, we have an object attached to a spring on a frictionless surface, which is released from rest, and then the spring extends a distance A. Just before the object is released, the total energy in the elastic potential is 1/2 Ka2. And then in B, when the object reaches position X, it has kinetic energy of 1/2 mv squared, and the elastic potential energy has decreased to 1/2 kx squared. We can then apply conservation of energy to derive an expression for the velocity of the object undergoing periodic motion as a function of position. Let's look at the object in the figure. As you can see in the top figure, it is initially at its maximum extension A and is then released from rest. The initial energy of the system is entirely elastic potential energy stored in the spring, 1/2 Ka squared. The object then moves towards the origin. In the bottom figure, it is at a new position X. Now part of this energy is transformed into kinetic energy, and the potential energy stored in the spring is reduced to 1/2 kx squared. The total energy of the system is the initial stored energy in the spring, 1/2 Ka squared. So we can set the two energies equal, and then we can solve for V. This expression shows that the object's speed is a maximum at X equals 0. And is 0 at the extreme position, X equals plus or minus A. Because the square root of the number can be either positive or negative, if the object in the figure is moving to the right, X is positive. If the object is moving to the left, then V is negative. So in this figure, we're looking at an experimental setup for demonstrating the connection between simple harmonic motion and uniform circular motion. And so let's examine this figure, which is a top view of an experimental arrangement that can help us visualize the relationship between simple harmonic motion and uniform circular motion. A ball is attached to the rim of a turntable of radius A, which is illuminated from the side by a lamp. We find that as the turntable rotates with constant angular speed, the shadow of the ball moves back and forth with simple harmonic motion. We can understand this by looking at the velocity equation. Let's rewrite it in terms of a constant c. This equation tells us that the velocity of an object moving with simple harmonic motion is related to the displacement. So in the figure, we're looking at a ball that is rolling with constant speed. And so in that case, if a ball is moving with constant speed v0 in the direction tangent to the circular path, at this instant, the velocity of the ball in the x direction is given by the expression shown. Let's now look at the larger triangle in the figure. We can write down another expression for sine theta. Let's equate the right-hand side of the two expressions for sine theta. We can solve for v. The velocity of the ball in the x direction is related to the displacement x in exactly the same way as the velocity of an object undergoing simple harmonic motion. The shadow on the previous slide therefore moves with simple harmonic motion. So here in the figure, we're looking at the drive wheel mechanism of an old locomotive, and you probably have seen these, maybe in person, maybe if nothing else in a movie or some kind of illustration of some sort like this. So here's an example of a simple harmonic motion in the photo of the drive wheel of a locomotive. The rods are connected to a piston that move back and forth in simple harmonic motion. The rods transfer the back and forth motion of the piston into a rotational motion of the wheels. A similar mechanism in an automobile engine transforms the back and forth motion of the piston to rotational motion of the crankshaft. So now let's talk about period frequency and angular frequency. The period t of the shadow in this figure from before, which represents the time required for one complete trip back and forth, is also the time it takes the ball to make one complete circular trip on the turntable. Because the ball moves through the distance equal to the circumference of the circle, 2 pi r, in the time t, the speed v sub 0 of the ball around the circular path is shown here with a period t defined as shown. Imagine that the ball moving from P to Q, quarter of a revolution, motion of the shadow is equivalent to the horizontal motion of an object on the end of the spring. So the radius A of the circular motion is the same as the amplitude A of the simple harmonic motion of the shadow. During the quarter of the cycle, the shadow moves from a point where the energy of our ball spring system is solely elastic potential energy to a point where the energy is solely kinetic energy. We can apply conservation of energy, and let's solve for A over V0, and then we can substitute it to get an expression for the period T. We see that the period is the time required for an object of mass m attached to a spring with spring constant k to complete one cycle of its motion. The square root of the mass is the numerator, so a large mass with mean will mean a large period, which agrees with our intuition. The square root of the spring constant k is in the denominator, so a large spring constant will yield a small period. It's also interesting that the period doesn't depend on the amplitude A. So the inverse of the period is the frequency of the motion. So the frequency of the periodic motion of the mass on a spring is shown here. The unit over frequencies are cycles per second, 1 over second or hertz. So here is the expression for the angular frequency omega. And the frequency and angular frequency are actually closely related concept. The units of frequency is in cycles per second, where a cycle may be thought of as a unit of angular measurement corresponding to 2 pi radians or 360 degrees. When we look at it this way, angular frequency is just a unit conversion of frequency. Radian measures is used for angles mainly because it provides a convenient and natural link between linear and angular quantities. So in our ideal mass spring system, the period is proportional to the square root of the object's mass. Experiments show that a graph of t squared versus m doesn't pass through the origin. This is because the spring itself has a mass. The coil of the spring oscillate just like the object, except that the amplitudes are smaller for all coils, but the last one. For a cylindrical spring, the effective additional mass of a light spring is 1/3 the mass of the spring. The square of the period is proportional to the total oscillating mass. So a graph of t squared versus total mass, which includes the mass hung on the spring, plus the effective oscillating mass of the spring, would pass through the origin. So here's a question for us. So an object of mass m is attached to a horizontal spring stretched to a displacement a from equilibrium and released, undergoing harmonic oscillation on a frictionless surface with period t0. The experiment is then repeated with a mass of 4m. Choose a new period of oscillation. The answer is 2t0. And so the period of an object spring system is t equals 2 pi the square root of m over k. Thus, increasing the mass by a factor of 4 will double the period of oscillation. So here's another one. So a mass of an object of mass m is attached to a horizontal spring stretched to a displacement a from equilibrium and released, undergoing a harmonic oscillation on a frictionless table. The experiment is then repeated with a mass of 4m. So compared to the original total mechanical energy, the subsequent mechanical energy of the object of the mass of 4m, and the answer is equal. The total energy of the oscillating system is equal to 1/2 ka squared, where a is the amplitude of the oscillation. Since the object starts from rest at displacement a in both cases, it has the same amplitude of oscillation in both cases. So here we're looking at a reference circle. And so we can look again at the relationship between simple harmonic motion and uniform circular motion. And if we look at the figure, which shows a ball at the rim of a rotating turntable of radius A, we can call the circle made by the ball the reference circle for the motion. Let's assume that the tunable revolutions at a constant angular speed omega. As the ball rotates on the reference circle, you can see that the angle theta made by the line OP with the angle with the x-axis changes with time. At the same time, the projection of P on the x-axis labeled point Q moves back and forth along the axis with simple harmonic motion. From the right triangle OPQ, we see that cosine theta equals x over a. So that means that the x coordinate of the ball is given here. Because the ball rotates with constant angular speed, we know that the relationship between theta and omega. So we can write our expression for x as shown. One complete revolution, the ball rotates through an angle of 2 pi radians in a time equal to the period t. In other words, the motion repeats itself every t seconds. Therefore, we can write an expression for omega as shown, where f is the frequency of motion, the angular speed of the ball as it moves around the reference circle is the same as our angular frequency of the projected simple harmonic motion. So we can rewrite our expression for x as shown in the bottom equation. So in this figure, we're looking at, in the first figure A, where we're looking at displacement. That's what we're focusing on. B, we're focusing on velocity. And C, we're focusing on acceleration, all of them versus time for an object moving with a simple harmonic motion under the initial conditions x sub 0 equals a and v sub 0 equals 0 at time 0. So this cosine function represents the position of an object moving with simple harmonic motion as a function of time. Top figure shows a graph of this function. Because the cosine function varies between 1 and -1, x varies between a and minus a. The shape of the graph is called sinusoidal. The middle figure represents a curve for velocity, and the bottom figure represents a curve for acceleration, both as a function of time. So we can derive, we're showing here the equation for velocity, and we can combine the equations. And now we can make use of the trigonometric identity and make some substitutions, and we get this result. We don't need the plus or minus sign anymore because sign can take both positive and negative values. So to derive the equation for acceleration, we start with the position equation and the equation for the acceleration, which was derived from Newton's second law. Combining equations and substituting omega squared, we get the following result. Notice that when the displacement x is at a maximum at x equals a or x equals minus a, the velocity is 0. And when x is 0, the magnitude of the velocity is a maximum. Also, when x equals plus x, its most positive value, the acceleration is a maximum. But in the negative x direction, when x is the most negative x position, x equals minus a, the acceleration has its maximum value in the positive x direction. So here we are showing an experimental apparatus demonstrating simple harmonic motion. Pen attached to an oscillating object traces out a sinusoidal wave on a moving chart paper. And so if we take a look at the figure, which shows an experimental arrangement that demonstrates the sinusoidal nature of simple harmonic motion, an object connected to a spring has a marking pen attached to it. While the object vibrates vertically, a sheet of paper is moved horizontally with a constant speed. The pen traces out a sinusoidal pattern. Okay, let's have a question here. So if the amplitude of a system moving in simple harmonic motion is double, which of the following quantities doesn't change? And the answer is the period. The expression for the total energy, maximum speed, and the maximum acceleration are E equals 1/2 KA squared, and V max equals A times the square root of K over M, and A max equals A times quantity K over M, where A is the amplitude. Are all are changed by an amplitude thus all are changed by a change in amplitude. The period of oscillation is T equals 2 pi the square root of M over K, and is unchanged by altering the amplitude. So now let's talk about pendulum motion. So in the figure, we see a simple pendulum consisting of a bob of mass M suspended by a light string of length L. So L is the distance from the pivot to the center of the mass of the bob. And so another system which exhibits a periodic motion is a simple pendulum, which consists of a small bob of mass M suspended by a light string of length L fixed at its upper end, as in the figure. By a light string, we mean that the string's mass is assumed to be very small compared to the mass of the bob, and so we can ignore it. When the bob is released, it swings back and forth, tracing the same path. But as a simple harmonic motion, we'll need to look at the restoring force, in this case, a force of gravity that acts on the pendulum. The pendulum bob moves along a circular arc rather than back and forth in a straight line. When the oscillators are small, the motion of the bob is nearly straight, so we can apply Hooke's law. In the figure, S is the displacement of the bob from equilibrium along the arc. Hooke's law is equal to F equals minus KX. So we are looking for a similar expression involving S, where F sub T is a force acting in a direction tangent to the circular arc. From the figure, the restoring force is shown here. Since S equals L theta, the equation for Ft can be written as shown. This expression isn't of the form F equals minus Ks. So in general, the motion of a pendulum is not simple harmonic. For the small angles less than about 15 degrees, the angle theta measured in radians and the sine of the angle are approximately equal. So if we take a look at the example for 10 degrees, this means that if we restrict the motion to small angles, our approximation that sine theta is equal to theta is valid, and the restoring force can be written as shown with this simplifying approximation. So you may remember that for an object spring system, the angular frequency is given by the equation shown here. Substituting the expression of K for a pendulum, we obtain the following relationship. The angular frequency can be substituted into our equation for displacement, which now mathematically describes the motion of a pendulum. The frequency is just the angular frequency divided by 2 pi, while the period is a reciprocal of the frequency. This equation reveals that's the somewhat surprising result that the period of a simple pendulum doesn't depend on the mass, but only on the pendulum's length and on the free fall acceleration. Also, the amplitude of the motion isn't a factor as long as it is relatively small. So here we have a figure showing simple harmonic motion for an object spring system, and it's analogous to the motion of a simple pendulum. So we're trying to show the analogy between the motion of a simple pendulum and an object spring system. And so there is a one-for-one relationship that you could see between them. You guys have all probably heard of Galileo. So Galileo was first noted that the period of a pendulum was independent of an amplitude. He supposedly observed that while attending church services at the cathedral in Pisa, The pendulum he studied was a swinging chandelier that was set in motion when someone bumped it while lighting candles. Interesting perspective there. So Galileo was able to measure its period by timing the swings with his pulse. Because of the dependence of the period of a pendulum on the free fall acceleration, we can use a pendulum as a timekeeper like a grandfather clock. Of course, these clocks are used at different locations on the Earth, so there will be some variation of the free fall acceleration. These types of clocks generally have some movable mass so that the effective length can be adjusted. Geologists often make use of the simple pendulum when prospecting for oil or minerals. Deposits beneath the Earth's surface can produce irregularities in the free fall acceleration of the region being studied. A specially designed pendulum of known length is used to measure the period, which in turn is used to calculate G, gravity. So although such a measurement in itself is inconclusive, it's an important tool for geological surveys. Okay, let's look at a question. So a simple pendulum is suspended from the ceiling of a stationary elevator, and the period is measured. If the elevator moves with constant velocity, and the answer is the period remains the same. If the elevator moves with constant velocity, the period of the pendulum is the same as that in a stationary elevator. So once again, same pendulum in an elevator. And the question is, if the acceleration, if it accelerates upward, the period, the answer is decreases. And accelerating an elevator is equivalent to a gravitational field. Thus, if the elevator is accelerating upward, this is equivalent to an increased effective gravitational field magnitude G, and the period will decrease. Similarly, if the elevator is accelerating downward, the effective value of G is reduced and the period is increased. Okay, so a pendulum clock depends on the period of a pendulum to keep correct time. Suppose the pendulum clock is keeping correct time, and then Dennis the menace slides the bob of the pendulum downward on the oscillating rod. The clock then runs, and the answer is slow. The reason the clock will run slow is with a longer length, the period of the pendulum will increase, thus it'll take longer to execute each swing. So each second, so that each second, according to the clock, will take longer than an actual second. The period of a simple pendulum is measured to be T on the Earth. If the same period were set in motion on the moon, would the period be? And the answer is that it would be greater than T. The value of G on Earth is about 1/6 of the value of G on Earth. So the period of the pendulum on the Earth will be greater than the period on Earth. Okay, let's look some more at the physical pendulum. So here we're seeing a physical pendulum pivoted at O. And so pendulum, however, can be made from an object of any shape, not just a mass on a string. The general case is called the physical pendulum. In the figure, a rigid object is pivoted at point O, which is a distance L from the object's center of mass. The center of mass oscillates along a circular arc, just as a simple pendulum. The period of a physical pendulum is given by the expression shown here, where L is the object's moment of inertia and M is the object's mass. As a check, let's take a look at the special case of a simple pendulum with an arm of length L and negligible mass. The moment of inertia is I equals ml squared. Substituting into our equation for the period, we get the expression expected result. So what about damped oscillations? And so here we're looking at a shock absorber that consists of a piston oscillating in a chamber filled with oil. As the piston oscillates, the oil is squeezed through holes between the piston and the chamber, causing a damping of the piston's oscillations. And then for B, one type of automotive suspension system in which a shock absorber is placed inside a coil spring at each wheel. And so you're seeing a shock absorber and another variation. And so in any real mechanical system, forces of friction retard motion. So the system doesn't oscillate indefinitely as in our idealized examples up to this point. The friction reduces the mechanical energy of the system as it passes, and the motion is said to be damped. A practical application of damped motion is a shock absorber in a car. A shock absorber consists of a piston moving through a liquid such as an oil shown in the figure on the left. The upper part of the shock absorber is firmly attached to the body of the car, as you can see in the figure on the right. When the car travels over a bump in the road, holes in the piston allows it to move up and down through the fluid in a dampened fashion. So here in the figure on the left, we have a graph of displacements versus time for an underdamped oscillation. And on the right, we have plots of displacement versus time for A, it's an underdamped oscillation, B, a critically damped oscillation, and C, an overdamped oscillation. So damped motion depends on the fluid being used. For example, if the fluid has a relatively low viscosity, the vibrating motion is preserved, but the amplitude of vibration decreases in time and the motion ultimately ceases. This process is known as underdamped oscillation. The position versus time curve for an object undergoing such oscillation is shown in the figure on the left. The figure on the right compares three types of damped motion with a curve A representing underdamped oscillation. If the fluid viscosity is increased, the object returns rapidly to equilibrium after its release and doesn't oscillate. In this case, the system is said to be critically damped, and it's shown in curve B. The piston returns to the equilibrium position in the shortest time possible without once overshooting the equilibrium position. If the viscosity is made even greater, the system is said to be overdamped. In this case, the piston returns to equilibrium without ever passing through the equilibrium point, but the time required to reach the equilibrium is greater than in critical damped, as illustrated by curve C. To make automobiles more comfortable to ride, and shock absorbers are designed to be slightly underdamped. You can demonstrate this by pushing downward sharply on the hood of a car. After the applied force is removed, the body of the car will oscillate a few times about the equilibrium position before returning to its fixed position. So here we're seeing a water drop. And so imagine dropping a pedal into a pool of water, or even a drop of water, as you can see in the photo. The disturbance produces water waves, which move away from the central point of the impact. If a leaf is floating near the disturbance, it will move up and down and back and forth about its original position, but doesn't undergo any net displacement from the disturbance. This means that the water wave or disturbance moves from one place to another, but the water isn't carried with it. When we observe a water wave, we see a rearrangement of the water surface. Without the water, there wouldn't be a wave. In the same way, a wave traveling on a string wouldn't exist without the string. Sound waves travel through air as a result of pressure variations from point to point. We can consider a wave to be the motion of a disturbance. In a later topic, we'll discuss electromagnetic waves, which don't require a medium. So consider this, what is a wave? And the mechanical waves we are discussing here require three things. First, they need a source of disturbance. Two, they need a medium. And number three, they need a physical connection or mechanism. A wave carrying energy and momentum, all waves carry energy and momentum, but the amount of energy transmitted through a medium and the mechanism responsible for the transport of energy are different in each case. For example, the energy carried by ocean waves during a storm is much greater than the energy carried by a sound wave generated by a single human voice. So let's look at the types of waves. And so in the figure, we have as a hand moves the end of a stretched string up and down with the red arrow, it causing a pulse to travel along the string. So if we take a look at the figures, which shows one of the simplest ways to demonstrate wave motion, the person flips one end of a long string that is under tension and has its opposite end fixed. The bump, called a pulse, travels to the right with a definite speed. A disturbance of this type is called a traveling wave. Each figure shows the shape of the string at 3 closely spaced times as the wave pulse travels along the string. Each segment of the string that is disturbed moves in a direction perpendicular to the wave motion. So, so the figure on the left shows the point for a particular tiny segment of the string P, that the string never moves in the direction of the wave. A traveling wave in which the particles of the disturbance medium moves in a direction perpendicular to the wave velocity is called a transverse wave. The figure on the right shows the formulation of transverse waves on a long string. So now we're showing a longitudinal wave across a stretch string. And so there's another class of wave called longitudinal waves, where the elements of the medium undergo a displacement parallel to the direction of motion. For example, sound waves in air are longitudinal. Their disturbances correspond to a series of high and low pressure regions that can travel through air or through any material medium with a certain speed. The figure shows how to produce a longitudinal pulse. The free end is pumped back and forth along the length of the spring. The action produces compressed and stretched regions of the coil that travel along the spring parallel to the wave motion. So here we're looking at Jupiter, one of our large planets in our solar system. And so waves are not necessarily only transverse or purely longitudinal. For example, ocean waves exhibit a superposition of both types. When an ocean wave encounters a cork, the cork executes a circular motion. Another type of wave called soliton consists of a solitary wave front that propagates in isolation. Ordinary water waves generally spread out and dissipate, but solitons tend to maintain their form. Solitons were first studied in 1849 when the Scottish engineer John Scott Russell noticed a soliton wave leaving the disturbance in front of a barge and propagating forward all on its own. The wave maintained its shape and traveled down a canal about 10 miles per hour. Russell chased the wave 2 miles on horseback before losing it. Now solitons are used to model physical phenomena, from elementary particles to the giant red spot of Jupiter. And you can see that in the picture here. You can see a rather different phenomena that's kind of distinctive. So in the figure, we're looking at a one-dimensional sinusoidal wave traveling to the right with a speed v. The brown curve is a snapshot of the wave at t equals 0. And the blue curve is another snapshot at some time later t. The figure shows a curved shape of a vibrating string. The pattern is a sinusoidal curve, the same as a simple harmonic motion. You can think of the brown curve as a snapshot of a traveling wave taken at some instant of time, say t equals 0. The blue curve is a snapshot of the same traveling wave at a later time. This picture can also be used to represent a wave on water. In that case, a high point would correspond to a crest of the wave and a low point to a trough in the wave. So here in the figure, we have in A, we have a longitudinal wave on a spring. In B, we're considering the crest of the waveform corresponding to a compressed region in the spring, and the troughs correspond to the stretch region of the spring. Same waveform can be used to describe a longitudinal wave, even though no up and down motion is taking place. Let's consider a longitudinal wave traveling on a spring. The top figure is a snapshot of a longitudinal wave at some instant, and the bottom figure shows the sinusoidal curve that represents the wave. Points where the coils of the spring are compressed correspond to the crest of the waveform, and stretch region corresponds to the troughs. So the type of wave represented by the curve in the bottom figure is often called a density wave or pressure wave, because the crest where the spring coils are compressed are regions of high density, and the troughs or where the coils are stretched are regions of low density. Sound waves are longitudinal waves propagating in a series of high and low density regions. So in the figure, one method for producing traveling waves on a continuous string is what we're trying to show, that the left end of the string is connected to a blade that is set vibrating. Every part of the string, such as the point P, oscillates vertically with simple harmonic motion. So the figure illustrates a method of producing a continuous wave or a steady stream of pulses on a very long string. One of the string is connected to a blade that is vibrating, and as the blade oscillates vertically with a simple harmonic motion, a traveling wave moves to the right, is set up in a string. The figure shows the wave at intervals of 1/4 of a period. Note that each small segment of the string now, such as P, oscillates vertically in the Y direction with simple harmonic motion. That must be the case because each segment follows the simple harmonic motion of the blade. That means we can treat every segment of the string as a simple harmonic oscillator vibrating with the same frequency as the blade that drives the string. The horizontal dashes represent the positions of the string when no wave is present. The maximum distance that the string moves above or below the equilibrium value is called the amplitude A of the wave. For the waves we will work with, the amplitude at the crest and the troughs will be identical. So look at the top figure. The horizontal arrows show the distance between two successive points that behave identically. The distance is called the wavelength lambda. So let's derive an expression for the speed of a wave. We start with the defining equation for the wave speed v. The wave speed is the speed at which the particular part of the wave, say a crest, moves through the medium. A wave advances a distance of one wavelength in a time interval equal to one period of the wavelength. So taking delta x equals to lambda and delta t equals to t, we have our equation for wave speed. Because the frequency is a reciprocal of the period, we can write this as shown. So let's think about plucking a string. So we'll turn our attention to the speed of a transverse wave on a stretched string. For a vibrating string, we need to consider two speeds: the speed of the physical string that vibrates up and down transversely to the string in the y direction, and the wave speed, which is the rate at which the disturbance propagates along the length of the string in the x direction. If a horizontal string under tension is pulled vertically and released, it starts its maximum displacement, y equals a, and takes a certain amount of time to go from y equals minus a and back to a again. This amount of time is the period of the wave, and is the same as the time needed for the wave to advance horizontally by one wavelength. Dividing the wavelength by the period of one transverse oscillation gives the wave speed. So if you consider the situation where the wavelength is a fixed length, then a string under a greater tension has a greater wave speed because the period of vibration is shorter. Remember that the wave advances one wavelength during one period. It also makes sense that a string with greater mass under period unit length mu vibrates more slowly leading to a longer period and a slower wave speed. The wave speed is given by the expression shown here, where F is the tension in the string and mu is the mass of the string per unit length, called the linear density. From this equation, we can see that a larger tension results in a larger wave speed, and a larger linear density gives a slower wave speed, as we expect. According to our equation, the propagation speed of a mechanical wave, such as a wave on a string, depends only on the properties of the string through which the disturbance travels. It doesn't depend on the amplitude of the vibration. So we can increase the speed of a wave on a stretched string by increasing the tension on the string. Increasing the mass per unit length, on the other hand, decreases the wave speed. So here we have an interference pattern produced by outward spreading waves from many drops of liquid falling on a body of water, say if there's rain. So you might be wondering what happens when two or more waves pass through the same region space at the same time. Two traveling waves can meet and pass through each other without being destroyed or even altered. For instance, when two pebbles are thrown into a pond, the expanding circular waves don't destroy each other. And in fact, the ripples pass through each other. In the same way, when sound waves from two sources move through the air, they pass through each other. In the region of overlap, the resulting waves is found by adding the displacements of the individual waves. For such analysis, the superposition principle applies. When two or more traveling waves encounter each other while moving through a medium, the resultant wave is found by adding together the displacement of the individual waves point by point. Experiments show that the superposition principle is valid only when the individual waves have a small amplitude of displacements, which is an assumption we will make in all of our examples. So in this figure, we're looking at constructive interference. If two waves have the same frequency and amplitude or in phase as in A and B, the resultant wave, when they are combined, C, has the same frequency as the individual waves, but twice their amplitude. So the two top figures show two waves of the same amplitude and frequency. And so we can imagine that some instance of time, these two waves are traveling through the same region of space. In this case, the resultant wave at the instant would have a shape like that shown in the lower figure. So for example, suppose the waves are water waves of amplitude 1 meter, and an instant they overlap, the crest means that the crest and troughs meet troughs, that the resulting waves has an amplitude of 2 meters. Waves coming together like this are said to be in phase and exhibit constructive interference. So now let's consider a case where there's destructive interfaces. So two waves A and B have the same frequency and amplitude, but are 180 degrees out of phase, so completely out of phase. The two top figures show two similar waves. In this case, the crest of one coincides with the trough of the other. So one wave is inverted relative to the other. The resultant wave shown in the bottom figure, if these were water waves coming together, one of the waves would exert an upward force on the individual drops of water at the same instance the other wave was exerting a downward force. The result would be no motion of the water at all. In such a situation, the two waves are said to be 180 degrees out of phase and to exhibit destructive interference. So if we consider two-wave pulses traveling on a stretched string in opposite direction passing through each other, so in this figure, it shows a constructive interference of two pulses moving towards each other in a stretched string. So we get that similar to what we had in this first figure. And so if we have two waves traveling in opposite direction with displacements that are inverted relative to each other, then in the figure, we see destructive interference. We notice in both this figure and the one on the preceding slide that the two pulses separate, their shapes are unchanged as if they had never met. So what about a reflection of waves? And so The reflection of a traveling wave at the fixed end of a stretched string. Note that the reflected pulse is inverted, but the shape remains the same. So far we've assumed that waves could travel indefinitely without striking anything. Whenever a traveling wave reaches a boundary, part of it or all of the wave is reflected. For example, consider a pulse traveling on a string that is fixed at one end. As in the figure, when the pulse reaches the wall, it is reflected. Note that the reflected pulse is inverted. So we can think about this case. When the pulse meets the wall, the string exerts an upward force on the wall. According to Newton's third law, the wall must exert an equal and opposite, that is, downward reaction force to the string. This downward force causes the pulse to invert on the reflection. So we're seeing here in the figure the reflection of a traveling wave at the free end of a string. In this case, the reflected pulse is not inverted. And so if we imagine a pulse arriving in a string's end and the end is attached to a ring of negligible mass and is free to slide along the post without friction, as shown in the figure, again, the pulse is reflected, but this time it is not inverted. When it reaches the post exerts a force on the ring, causing it to accelerate upward. The ring then returns to its original position by the downward component of the tension in the string. When a pulse reaches a boundary, it's partly reflected and partly transmitted past the boundaries into a new medium. So let's take a question. So two identical springs are attached to two identical masses. Both are resting on a frictionless horizontal surface. One of the springs displays a distance d from its equilibrium position, while the other displays a distance 2d. If both masses are released at the same instant, which of the springs, A or B, returns to an unstretched length first? And the answer is it's a tie. And so the period of oscillation object of mass m attached to a spring of constant k is 2 pi over the square root of m over k. Note that the period does not depend on the amplitude. It takes the same amount of time to complete one large oscillation as one small oscillation. In both cases, the block is undergoing 1/4 of a complete oscillation, so the time required is 1/4 of a period. So that's what that means. So three systems are constructed from identical springs and masses as shown. Which statement is true regarding the frequency of these systems? And the answer is ω1 is equal to ω2, which is equal to ω3. I'm going to leave that up to you guys. You can do a little bit more evaluation of that offline, just due to the time. So we'll have this figure and then we'll go on to the next chart. So here we have a couple of figures here. And so the phenomena of interference is a result of, and the answer is superposition. Okay. The sound waves can interfere, and the answer is none of the above. So I'm just going to skip over those and just give you those answers. And sorry if I'm not giving an explanation, but this lecture is already getting long. I'm going to just go ahead and do the summary now, and then we'll call it a lecture. So here we have Hooke's law for simple harmonic motion occurs when the net force of an object along the direction of motion is proportional to the object displacement in the opposite direction. This equation is called Hooke's law. The time required for one complete vibration is called the period of motion. The reciprocal of the period is the frequency of the motion, which is the number of oscillations per second. When an object moves with simple harmonic motion, its acceleration as a function of position is given here. And then for elastic potential energy, the energy stored in a stretched or compressed spring or in some other elastic material is called elastic potential energy. The velocity of an object as a function of position when the object is moving with simple harmonic motion is given in this equation. Then for concepts of oscillation rates in simple harmonic motion, the period of an object of mass m moving through a simple harmonic motion while attached to a spring of spring constant k is t, where t is independent of the amplitude a. The frequency of an object spring system is f equals 1 over t. The angular frequency omega is given here, and the units are radians per second. And for position, velocity, and acceleration as function of time, when an object is moving with simple harmonic motion, the position, velocity, and acceleration of the object as a function of time are given in the equations shown on each graph. So for a motion of a pendulum, a simple pendulum of length L moves with simple harmonic motion for a small angular displacement from the vertical with a period of given by the expression shown. Waves in a transverse wave, the element of medium move in a direction perpendicular to the direction of the wave. An example is a wave on a stretched string. In a longitudinal wave, the element of the medium moves parallel to the direction of a wave velocity. An example is a sound wave. And for frequency, amplitude, and wavelength, the relationship among the speed, wavelength, and frequency of a wave is given here. The relationship holds for a wide variety of different waves. And for the speed of waves on strings, the speed of a wave traveling on a stretched string of mass p per unit length m and under tension F is given here. In terms of interference of waves, the superposition principle states that if two or more traveling waves are moving through a medium, the resultant wave is found by adding the individual waves together point by point. When waves meet crest to crest and trough to trough, they undergo constructive interference. When crest meets trough, the wave undergoes destructive interference. And then for reflection of waves, when a wave pulse reflects from a rigid body, the pulse is inverted. When the boundary is free, the reflected pulse is not inverted. Okay, well, that's going to be it for our lecture here. So thank you very much.